In physics, you're taught that scalars are just amounts, while vectors have a direction. But that standard classroom definition actually has a major blind spot. Take electric current. It clearly flows in a specific, defined direction down a wire. Vectors require a magnitude and a specific direction, while scalars only need a magnitude, combining through ordinary algebraic rules. But true vectors have a strict, non-negotiable requirement. When combining them, the exact angle between them completely changes your final result. This strict geometry test is the law of vector addition. So what happens when we apply this test to electric current? It has an amount and a clear flow direction. But watch when two currents collide. No matter how sharply these two wires angle into the junction, their combined output ignores the geometry entirely. 3 amps plus 4 amps will always equal exactly 7 amps out. And that electric current flowing down the wire from the very beginning, because it completely fails the geometric rules of vector addition, it remains strictly a scalar.
A unit vector captures pure direction. But how do you mathematically strip away a vector's length without changing its path? Take a standard 3D vector, vector A, stretching across an XYZ Cartesian grid. First, we calculate its exact total length by combining its x, y, and z components. That 3D math gives us the Euclidean norm. But this calculation just gives us a single number. The vector itself is still a full-sized coordinate arrow. How do we neutralize that size? We divide the original vector by its own calculated length. Because we're dividing a magnitude by itself, the arrow scales perfectly backward along its original trajectory, shrinking down until its length equals exactly 1. This new arrow receives a hat symbol over its letter, identifying it as a pure directional pointer that won't artificially inflate other equations. And what about that original massive vector A that was stretching all the way across our grid? It has been perfectly distilled into a standardized 1-unit directional arrow, permanently locking its path.
How does the dot product take two arrows pointing in different ways and combine them into a single directionless number? Think of calculating work in physics, a force vector pulling a heavy box along a specific distance vector. To measure their alignment, we cast a perpendicular shadow from the force straight down onto the distance. Any upward pull doesn't move the box forward. How do we strip away that useless perpendicular effort? Enter the geometric formula. Multiplying their magnitudes by the cosine of the angle perfectly scales the force down to only its overlapping parallel shadow. No angle? Use the component form. Just multiply their matching x, y, and z coordinates and add them up. You get the exact same scalar result. And if the vectors are perfectly perpendicular, they cast no shadow, meaning their dot product is exactly 0. So back to our moving box. By dotting the force and distance, we isolate the useful effort, extracting the exact scalar work done.